All right, so this is going to be a quick one and not the subject that I planned, but welcome to day 3 of Inktober Engineering Challenge. And end of the day, sitting here at home. So I'm going to go off the unplanned topic, just talk about something I can do quickly. Just want to start thinking about what the overall form and structure of the machine will be. If we talk about the product, we've talked about the finished product that it produces, and you can imagine it as when we talk about just the volume that it could occupy. It could be potentially a cylinder, or inscribed within that, it could potentially be a cube. So we're talking about the maximum volume that the machine can produce, and how would we decide, what that will be? If we look at from the top view of the machine, in general, if we're limited by, a long dimension, so we have a structure, we have some kind of space constraint that limits us to this long dimension L. If it's a cylindrical form, that's the maximum volume for that constraining dimension L. If we go with a rectangular or square form rather, then for that same limiting dimension L, of course, we have a smaller volume. So it would make sense to go with a cylinder if in that sense. Again, this is being driven by an external constraint imposed on us of that maximum dimension there. And as we, if we were to build then our chamber around that, it's nice and symmetric. There are a lot of reasons to like a cylindrical structure in engineering. It's got that nice symmetry. It's rotationally not only fully, about halves, or it's rotationally symmetric about any segment theoretically. So it's really easy to do such things as, break it up into 120-degree segments and use kinematic mounting. The heat flow, heat distribution generally be nice and uniform. I mean, you might get temperature differentials, but again, they'll be at least concentric. They'll be circular. In terms of sag, if we look at this, if an end view, if we were to have, that structure here and do a section through it, we still get deflection if we have gravity or some pressure, applied across that surface, but at least the deflection is symmetric. And you can even do such things as you could, knowing that it would assume this shape, you could actually define a structure that when it sags under gravity, or when you apply a known load, rather than being bowed like this, it actually assumes a flat shape. So those are some of the things that are relatively easy to do when you have a symmetrical system, that are not when you have a rectangular system. Similarly, if there is a pressure, so if this is a pressure vessel, and we are dealing with a pressure vessel, so if you have pressure internally here inside the chamber, then the chamber will bow, but it will tend to bow uniformly. And so as well, the orientation between the bottom and the top will remain pretty much the same. So if you were to have components mounted on the top pointing at the bottom, they would remain largely pointing in the same direction as you go to put pressure in there. Conversely, if we were to, the same thing works if we were to evacuate that. So instead, if we've got vacuum going on, It's just going to assume the opposite shape. So we draw a vacuum. We're still going to deflect, but again, it's going to be a uniform deflection, and the top and the bottom will deflect, but you have that great symmetry that gives you all kinds of benefits. So that's why it's nice. Something, if you were to have, well, I'll just leave it there. Now, theoretically, if you were to have a rectangular structure, you might have some of the same, and you were to support it on a central post somehow, you might get a similar behavior. You could certainly predict it. It would still be a deterministic problem. You would be able to solve it and know what the deflection of this would be as you change the pressure internally, but it would be a more complicated problem. And even though you can calculate it, doesn't necessarily mean it helps you, solve the problem that you're dealing with. So in a lot of senses, the natural case for this, is okay, it'll be round. It will make our life easy in a lot of ways. But that's, again, assuming that we're trying to maximize volume for a given cross-section. In that case, round is it. But we have other considerations here. So, namely, we have to spread. We have what was described as the spreader the other day. That's going to be moving across. Some opening, and that opening is more or less what we're trying to define. And the purpose of that is to drag this particulate and spread it evenly across that opening. So there may be, if you think about the most obvious design for this spreader, it's linear. And the most obvious direction for that movement is perpendicular to that. So it's going to spread the material in a rectangle. So even if you were, so it no longer makes sense from that point of view to have a circle as your optimum cross-section, because there's something else in the system that's saying this thing has to be square. I know it's very simplistic, but this is, it's a very high level kind of fundamental decision. Could you do other ways to change that? Perhaps, but again, as we discussed yesterday, there's going to be quite a bit of complexity and tuning to get the uniform thickness and good coverage and complete 100% coverage over this area as we go across. So why make it more complicated? That's one of these cases. This is not to say you don't explore other variations of this design, but as a first starting point, and as we start to conceptualize it, having that kind of rectangular cross section kind of starts to make sense. As we look at it from above. We have, we're going to be moving left to right here and spreading. It's going to have a park position on the other side. And so we're going to have, it's just going to make sense to maximize the possible area that is available to use. You want to maximize that since you have that same footprint in the machine no matter what. It just makes sense to make it square. And as another aside, as we start to think about throughput on this machine a little bit, you can imagine perhaps we want to cycle back and forth. So we have a supply of powder over here that we spread on pass 1. And then to minimize or maximize our throughput, we have another supply of powder over here. And we spread it, when once this layer, that pattern, whatever it's going to be, is drawn by the laser in that layer, then we reverse for a pass 2. And in that case, we're saving a little bit of time in terms of we don't need to drive it back and start from the same direction every time. So that's a possible thing, is that might make sense, but is it worthwhile? Does that save us time? Really save time, and a significant amount of time. And then, well, because if it takes 10 minutes, and I'm sure it's not 10 minutes, but let's use something a little more realistic. Depending on the complexity, if it takes 1 minute to draw a layer, and it only takes 5 seconds, not even 5 seconds, 2 seconds to reverse the direction, maybe we'll make this 0.5 minutes, something a little more reasonable. And it only takes 2 seconds to return it to the original position. Over many, potentially, over 1,000 layers, that costs you 2,000 seconds. But that's versus in a total of 1,000 layers times half a minute. So 30,000 seconds. So is that worth it? That time savings? And then the other question is, the real answer to that question depends on the way the real question you're answering is it worth the complexity? Because if you are doing this setup where you have 2 supplies of powder, then you need 2 mechanisms for that. You need 2 ways to remove the waste powder. We talked perhaps about the spreader having an angle, a certain angle that it operates at. Well, if that is critical, then we need to reverse that angle in order to go back and forth. So you just need to explore it and say, come up, answer early on, yes or no. Is it going to be worth, is that time savings, the estimated time savings worth, all of that extra complexity? Let's see. So just some other thoughts that occur to me. Now, as we have, again, I'm not definitively saying that this is the only way to go. And I wouldn't rule out other ways of spreading. Again, that would be maybe you spend a day or two to brainstorm ideas around how to spread that. You'll probably end up doing multiple sessions on the spreader and a different overall, very high level, the basic form that it might take. Is there possibly some way to do a rotary spreader from out here? Just throwing and brainstorming, there's supposed to be no bad ideas. I don't like that, but there are other concepts that might justify something other than a rectangular build area, but I'm having a hard time imagining them. But you're not going to rule them out automatically. But if we use this assumption that we have a rectangular build area, well, then the question becomes, what is the structure around it? And now, if you want the most space efficient structure, that structure would be rectangular as well, in all likelihood. However, as we mentioned, there are a number of issues with, it's not a number of issues, it's just suboptimum in some ways to have that rectangular structure. So perhaps if you have the space available to you, you still want to have a circular structure. So that's a possibility. That's a trade-off. Now in this case, though, your circular structure is actually a little bit less space efficient. Because once you've already settled on a rectangular shape, then putting a rectangular structure around it is the most space efficient. And if you were to put a round structure on it, because of the advantages of that symmetry and maybe ease of fabrication, you can make it from a single part. Now you have all of this waste space. And that's non-trivial. Again, there are a number of costs associated with a larger machine. One is, floor space in a flat factory. And another one is time, actually, because if we are, again, we've already established that this is a pressure vessel of some kind. So we have to pump it down to vacuum at one point, and then we're going to backfill it to some partial pressure with argon or something like that. The larger that volume is, the longer it's going to take to pump down. So that's another throughput. So those are just some general considerations. Can't answer them right now, but as what we would do in normal and consulting scenario, we'd spend a few days with the client working on making sure that we have the right understanding of the requirements, go away, generate some ideas ourselves, and then kind of down select and make our presentation. So it would be in that phase where you wouldn't want to rule out any particular architecture right away. But you want to have this kind of very high level discussion and think through. As what I said on Inktober the first day, we sometimes are over relying on CAD and modeling things up, but a lot of this can be resolved on the whiteboard, just like this, or on a tablet. So I'm going to wrap it up today. Hopefully start earlier in the day, not have a cold tomorrow, and get back to the whiteboard drawing. But on the other hand, I think that it was nice to have a much shorter video this time. I hope you got something out of it.